Hey, hi, 2.5. The ready has you rewriting these radical expressions. They're so radical and cool, dude. Oh man. To remove perfect square factors such as 4 and 9, 25 and 36 and 49 and 64. Occasionally you'll see 81, maybe even 100, maybe even 121. Those are all perfect square factors. You may want to write them down in case they come up again. Maybe pause the video right now, write them down. Okay, so when we're rewriting these radicals, we're aiming to have one of these numbers as a factor. We might not want to just go for the default numbers we're aiming for or think of. We might want to be a little strategic, but fall back on these numbers or try to have them happen. Okay, capiche? Sound good? So let's get to it. What's happening here? We have 40, square root of 40. We could rewrite that as 4 times 10, and then rewrite that as square root of 4 times square root of 10. That's safe, right? What's the square root of 4? It's just 2. So I could take this further and just write 2 square root of 10. And I think that would be good, don't you think? Another way, and you could actually take this further, to be honest with you, you could have rewritten this as, oh, never mind, you wouldn't want to do that. That'd be ludicrous. That's fine. Then you can keep that as is. Let's keep it going. Square root of 50. We definitely could rewrite that as square root of 25 times square root of 2. Square root of 25, we know that, right? That's a perfect square. It's just 5. 5 times square root of 2. This is the most simplified way to write square root of 50. It has a decimal with it, but we're not trying to get to that right now. So let's keep going. Let's find one that's a little bit more challenging. Let's try 3. So we're taking the cubic root. I know it's a cubic root because that's 3. So we're taking the cubic root of 54. So really, we're aiming for some term, like we said previously a perfect square, but now we're looking for a perfect cube, like 8, because you can get 2 times 2 times 2. Another version of a perfect cube would be 3 times 3 times 3, which is 27. Also 4 times 4 times 4, which is 64. So these are other examples of perfect. They're so perfect cubes. And we're going to try and aim for something like that in here because we're taking a cubic root. Let's see. 27 is a little bit too high, maybe, but let's try it. So we can rewrite this as the cubic root. 27 actually is divisible, but 54 has 27 as a factor. So let's entertain this. 27 times 2 would get you there. So we could rewrite this as the cubic root of 27 times the cubic root of 2. Cubic root of 27 is 3. So we can rewrite this as 3 times the cubic root of 2. And we're done. So that's the simplified way we would write that. Capiche? Any questions on those? With the other ones, with this exception of 3 and 5, those are perfect squares you'll look for. So those I don't think are too bad. 10's kind of cool. We're modeling the 3 to the x power, where every time it moves forward, it keeps multiplying by 3. So 9 times 3 will get you 27. But what happens if we move backwards? If we're moving backwards, normally we're always moving to the right, but what happens and what could we say is going on in this pattern if we're moving to the left, could say that you're dividing by 3. 27 divided by 3 is 9. 9 divided by 3 is 3. 3 divided by 3 is just 1. And we're going to show what this could mean for 3 to the negative 2. Well, if we keep going, same song and dance, 1 divided by 3 is just 1/3. And if we divide by 3 again, you can use a calculator or use fractions, but eventually it's 1/9. And isn't this just 1 over 3 squared? And 3 squared is 9. So wouldn't that make this next one 1 over 3 cubed? Or 1 over 27, some might say. What do you think? So how could we use this to explain the meaning of 3 to the negative 2? Good question. Well, 3 to the second is in the denominator. And since it's in the denominator, this 1 over 3 to the second could really just be rewritten as 3 to the negative 2 power. Because if we have a negative fraction or negative exponent like this, we can rewrite it as a fraction. So that kind of explains it. For 11, if two expressions with exponents are a perfect match, except one has a negative exponent, so one of the terms has a negative exponent and the other has a positive exponent, like 5 to the third and 5 to the negative third power, how does the exponent change the meaning of the expression? Well, 5 to the third is just 125. This isn't rewritten as a fraction. However, if we have 5 to the negative third power, we could rewrite that as 1 over 5 to the third. And if we're so inclined, we could take it further to 1 over 125. So the exponent, if it's negative, can be rewritten to a fraction. That's a good thing to make a note of. If it's a negative exponent, consider making it a fraction. Let's keep this going. We will now start to rewrite these with only one positive exponent. We're a fan of negative exponents, but now we're aiming for positive ones. So let's do this. 3 to the negative 8th power. I know it's a negative exponent, so that means I can flip it and rewrite it like that. Done. Simple enough, right? Let's see what else we got. We have 1/7 to the negative 4th power. Okay. So we just take that whole fraction, put it down here. And then if we're really feeling crazy, we're dividing by a fraction. So we could say that this is 7 to the 4th power. Both of these work just fine. This is definitely a little bit cleaner though. If you're not too sure what's happening here, we're dividing by a fraction. So we could really just take the reciprocal of 1/7, which is 7 over 1, and 4 is along for the ride. There you go for those. We'll do 17 as well. We have parentheses. What do? Hop the fence. So this is x to the negative 12th power, which we can rewrite as 1 over x to the 12th with a fraction. There we go. The Go just has you plugging in numbers for parts A and C. Use a calculator if you'd like. We'll see what B is all about though. So we have this function and I'm going to leave A and C for you. B, let's look at B. Find x if f of x equals 21. So they're saying that the outcome here's 21. So just replace it. And does this look like something we could solve? Perhaps with SAD MEP. I think it is. Let's see that we have a -7. So let's add back 7 here and here, getting us 28. 7's canceled. 2x equals 28. We see multiplication, but we want to do it with division. Divide by dose. 28 divided by dose. 14. So this should almost seem like a throwback, because if we had a table of x and a table of f of x, if we just knew that the outcome over here was 21, we could, based off of the equation, backtrack and say that our x input is 14. I hope that this video was helpful. If you have any questions, holler, let me know. Thanks for watching.